I'm gonna go ahead and start on time today. I hope you guys are well. Good morning. Okay, so today we're gonna talk about E1 and E2 reactions. But before we do that, I want to kind of do a mini review of what we talked about on Monday, so SN1 and SN2 reactions. So first, SN1 reaction, again, SN1 reaction involves two steps, where step one is the leaving group leaves and creates a carbocation, and I'll show you an example with this reaction right here, right now. And then the step two, right, you have formed your carbocation, and step two, the nucleophile will attack the carbocation you just formed. So again, two steps. And then nucleophile that attacks the carbocation, that one will involve a weak nucleophile, most likely, which is how you can kind of compare it to SN2, which we'll talk about right now. SN1 reactions prefer tertiary carbons, right? Because again, we're forming a carbocation and we want that carbocation to be stable, and it's more stable when it's tertiary carbocation. And then the rate, again, it's kind of in the name itself, SN1 for unimolecular. So unimolecular, one molecule, right? So one molecule is involved in the rate, in dictating the rate, and that's going to be the alkyl halide. So this is the alkyl halide in this example right here. And again, that's what dictates the rate, because the alkyl halide has the leaving group, and that leaving group is the one that's going to leave to create the carbocation. So that step is slow, so it dictates how fast or how slow this rate is going to be. And again, if we see this reaction here, we can see our alkyl halide and our nucleophile. H2O is a weak nucleophile, so I kind of said that these involve weak nucleophiles. So let's do this example right here. Feel free to stop me if you have any questions. If I'm going too fast. Make a comment, anything. You don't understand my handwriting, feel free to stop me. But okay, let's do this one. Again, SN1 involves two steps. The first step being the leaving group leaves. Let me make this black. The leaving group leaves. So CO is our leaving group, it's gonna leave. We're gonna create a carbocation. This is our carbocation. And you can see this is gonna be planar, right? So CH3 used to be a dash, now it's just kind of a line because it's in the same plane as the hydrogen and as this right here. So now it's a plane, and that is important because H2O, right, which is our nucleophile, is going to come and attack, or come and attack this carbocation, but it can attack from the back or the front. Again, it's planar, so hopefully you can see my hand. So let's say it's planar, right? So it can come from the back or the front. So you can have two different products because of that fact. So let's just draw the arrow. I'm sorry if my arrow is wonky. It's going to attack that carbocation right there. And you're able to, again, come from the back or the front. So you're able to have two different products as the H2O attacks. So let's draw that. First off, this is what if the H2O attacks from the front. So let me draw those H's. It's going to be a positive right there. Dash, it's going to be CH3. And then if it attacks from the back, then the H2O that is being attached is going to be a dash. So let me draw that. Positive charge. And then there's going to be our CH3 that was there. Is there any questions so far how I got these two? Again, these are just because it can attack from the back or the front. So we can see the H2O that's being attached both wedge and dashed. And then, so this was the first step, right? The leaving group, leaving. This is the second step where that nucleophile attacks. Here there's an extra step because there's a positive charge on this molecule right here, and we want to remove an H so that it's not positive charge. So you can use an H2O, or in this case, I'm just going to use a Cl minus. Draw those there. I'm going to take that H, those electrons from that bond are going to go to the oxygen, right? So in this case, this one's going to become this product right here, where you have an OH and the wedge and the CH3 in the back. And then we can do the same thing to this one right here. You remove that H. Those electrons from right here are going to go to the oxygen, and then this becomes this one right here. So you can see we have two products. These are enantiomers to each other. And hopefully you guys are able to take in what I've just drawn, so let me not erase this too soon. But we have what is retention and inversion of stereochemistry. So if we look at where the CO is right here, this product right here, right, because we have two products, this product right here is retention of stereochemistry, and this one over here, as compared to this one, right, the CO is here is wedge, over here the OH is dash. This is inversion of stereochemistry. So you have two molecules that are enantiomers, and these two are both inversion and retention of stereochemistry. So does anyone have any questions for SN1 right now? So now let's review a bit about SN2 reactions. Again, SN2 reactions are considered reaction, meaning the steps happen at the same time. And because they happen at the same time, you don't have a carbocation. So you don't have to worry for SN2 about methyl shifts or hydrogen shifts because there's no carbocation formation. And SN2 requires a strong nucleophile as opposed to SN1 that required a weak nucleophile. And this prefers primary over secondary over tertiary, which is opposite of SN1, right? And the reason why SN2 prefers primary is because it's going to have a nucleophile attack, do a backside attack. And if there's too many things surrounding that carbon it's going to attack, then those are going to kind of be a barrier for it to attack. So it's really not going to want to be in a tertiary. It's not going to want to occur with a tertiary because there's going to be too much steric hindrance around there. And I could draw an example of what I mean. So let's say there's a leaving group CO here. We have 3 methyls around it. And I'm going to draw the H's. This. You guys can see that, but it looks kind of like a little tree branching out, right? If we have, let's say, a nucleophile trying to attack from the back, right? Because it's going to occur a backside attack. There's too many like methyls or like hydrogens from the methyls kind of like hindering that from happening. So that's why it would prefer having a primary, which would have less of this branching, right? Because that's going to be easier to attack from the back. Does that make sense? Does anyone have any questions? And again, SN2 is bimolecular, meaning 2 molecules are involved in the rate, one being the alkyl halide and the other one being the nucleophile. And let's do a quick example here. Let me zoom in over here. So we have what is our alkyl halide right here, and a nucleophile right here, which is the CN minus. This is a concerted reaction, so really what's going to happen is that the nucleophile is going to do a backside attack. But first, we have, let's look at this molecule right here. The Br is the wedge, right? There's also an H that is dashed in the back that is hidden, right? So what's going to happen is that the Cn is going to attack from behind between that H and the CH3 right here. And what's going to happen is that it's going to push this H that's a dash forward. And then also while this Br leads, right? So what's going to happen is that slowly, right? Well, not slowly, but the Cn is going to come from the back, push that H to the front to where Br was at, and Br is going to leave. So what's going to end up being the product? Let me zoom in over here. Is that, again, the Cn came from the back, so it's going to be a dash now. It's going to replace where the H was from. Let me redraw that H right here. And the H was pushed forward, so now the H is that wedge right there. Does that make sense? Let me redraw this line through. That's what happened right there. Is there any questions on this? And again, Br left, so Br now is an ion, right? Because it took those electrons, and it's in solution with Na+, and the Na+ comes from that was with our nucleophile. Is there any questions so far? Okay, I'll take that as no questions. So now that we have done a little bit of review, let's go over new topics. Today, again, we're talking about E1 and E2 reactions. And what the E means is elimination. So we're going to be talking about elimination reactions. And essentially, elimination reaction, if we look at this part, this reactor, I forgot the actual name, this right here that's going to react, we have our leaving group attached to this carbon, right? And then this carbon right here, we're going to call this alpha carbon. So the alpha carbon is going to be where the leaving group is attached. So the leaving group is attached here. This is going to be the alpha carbon. The carbons that are right next to this alpha carbon are going to be beta. So these two are going to be beta carbon. And then the hydrogens attached to these beta carbons are going to be called beta hydrogens because they're attached to the beta carbon. So now that we kind of know what these are named, an elimination reaction is essentially the removal of a beta hydrogen. So a removal of this blue hydrogen or this green hydrogen here by a base. So this B right here stands for base. And that kind of removal right here, there's going to remove the H, and then also the Br is going to leave. And then with that, there's going to be a formation of a double bond. And there's two ways that the leaving group leaves that we'll talk about. This is kind of what separates E1 and E2 reactions. So I'm not going to go into too much detail, but just know that we removed an H, in this case, we removed this green H right here from this green beta carbon. And we also have this Br leave from this that is attached to this alpha carbon. And there was a formation of a double bond between that beta carbon and that alpha carbon. So right here. Okay. And I'll talk more about the mechanism and how it occurs. This is just kind of the main idea behind this. So before we go into the mechanism, I kind of want to talk about something that's called the Zaitsev rule. Essentially what this means, right? We had talked about alkene stability, and we had said the more substituted the alkene is, the more stable it is, right? So in this case, this tetra is more stable because it's more substituted. So in this case, Zaitsev rule is just kind of saying because alkenes, that are more substituted are more stable, they're more likely to be a product, right? Because in elimination reactions, we're forming alkenes. So the more substituted those alkene is, the more likely the product is going to be if we do have more substituted alkene because it's more stable. So if we go back to this example right here, we can see that we formed the double bond between these two, and that was because we would have a tetra substituted alkene if we did form it between these two, as opposed if we use these beta hydrogens. And we'll go more with the examples, but let me just draw what it would look like if we had instead kind of formed that double bond between this one right here, this alpha carbon and this beta carbon, and removing this H right here. Instead, it would have not been a tetra, it would have been a tri-substituted. So let me just draw it real quick. Hopefully that's not too ugly, but so you can see that C3 and H. So instead of being tetra substituted, it is just tri-substituted. One has three kind of carbons attached to the double bond. Does that make sense to everyone? Which is why in this case we formed this one, because this one's tetra as opposed to this one that's tri. So whenever we're looking at elimination reactions, we want to follow Zaitsev rule, essentially form the double bond where it's more, the alkene is going to be more substituted. Any questions? So there is kind of like a shortcut into thinking of which hydrogen to use. And again, we'll talk about how the mechanism occurs, but whichever hydrogen we remove, so like let's say we remove this hydrogen, right? And then that carbon right here, that where the H was removed, that is where the double bond is going to be formed. So in this example, that's right here, we removed this H, so the double bond was formed between these two, between this beta where the H was removed and this alpha carbon where the Br left. So in order to know, like, how do we know which one's going to follow Sate's rule, like which hydrogen to remove to know like what to form? So there's a shortcut into thinking about that. So we look at the alpha carbon, and then we have the beta carbons. And again, we want to focus on the beta hydrogens, so these hydrogens right here. So in order to know which hydrogen to remove from which beta carbon, right, because we have two options. We have these two beta carbons. Usually it's easier to think of using the carbon that has the least hydrogens because that will lead to the Sate's rule. So this has one hydrogen attached versus this beta carbon that has two hydrogens attached. If we remove this H because there's less H's in this carbon, this will lead us to following Sate's rule, essentially a more substituted alkene. So this is essentially what's saying you can just focus on which beta carbon has the least hydrogens and focusing on removing that hydrogen in order to form Sate's product or may have a product that follows Sate's rule. Does that make sense to everyone? You can also just kind of draw both ways and see which one will give you Sate's product, which one's going to lead to a more substituted alkene. But this is just the easier way, just looking at which beta carbon has the least hydrogens and removing that hydrogen that's attached to the carbon that has the least hydrogens. Does that make sense to everyone? Any questions? You guys are good? Okay, let's move on. So now we're going to talk about the actual E1 reaction and the mechanism of it. So you're going to notice some similarities between SN1 and E1, right? So let's similarly, sorry, let me start again. So I have some main points here to focus on when we're looking at the E1 reaction. So first, similarly to SN1, like SN1, we know it involves two steps. In this case of E1 also involves two steps. The steps are kind of similar but different, right? Because E1 is a formation of an alkene. So in step one, we're gonna have the leaving group leave, similar to SN1, and form a carbocation. So we have that carbocation. In E1, the step two is gonna be removal of a beta hydrogen and the formation of that double bond. Okay, so again, similarly like SN1 reactions, we had talked about that SN1 reactions involve weak nucleophiles. This is similar in that it involves weak bases. And notice how this is base, not a nucleophile. So we know that nucleophiles and bases are similar, right? But they're still separate. In this case, we're focusing on basicity because again, that base is the one that removes the H, right? So we know bases accept hydrogens or protons. So in this case, we're focusing on basicity. So E1 involves weak bases, such that in this reaction right here, H2O, H2 is a weak base. So E1 involves weak bases. And similarly, like SN1, this is a unimolecular reaction such that we're only going to focus on alkyl halides for knowing the rate, right? So we're only going to focus on alkyl halides. And again, similarly, like SN1 reactions, we also prefer tertiary over secondary over primary. Again, because here in step one, we're still forming that carbocation. So we know that carbocation wants to be stable, so it's going to be more stable with the tertiary carbon. Okay, is there any questions so far? Okay. So this is an example of the reaction. We'll go into the mechanism. but mainly, again, there's a weak base. We have our alkyl halide. This Br right here that's gonna leave is in a tertiary carbon, right? 1, 2, 3. So we're good in that aspect, right? If this were to be a primary, right, we know that wouldn't really occur because a carbocation is not stable in a primary. So in this case, we're good that this is tertiary. We have a weak base. So let's look at how the mechanism works. So first step, again, we're gonna have the Br leave, or our leaving group leave. So we're gonna have an arrow from this bond right here to the Br, because the Br is gonna take those electrons. And as it does that, it's gonna form a carbocation. So that's that. You can see the arrow right there. And now we have our carbocation right here. The next step will be focusing on the base and where the base is going to remove that H from, right? So again, if we do what I had talked about and kind of looking at which beta carbon, so again, this is an alpha carbon right there. That's the sign for alpha. This is beta carbon, and this is also beta carbon. If we look at how many hydrogens are attached to each beta carbon, then we can kind of see which hydrogen to take to form the double bond. So this one right here has 2 hydrogens. This beta carbon right here has 1 hydrogen. So we want to remove the H that's attached to the beta hydrogen that has the least hydrogens. So in this case, we're going to remove this H, and that's going to lead us to our stated product, which is a more substituted alkene because we're forming an alkene. So in order to form that alkene, this base right here is going to come and remove that H or take that H. Those electrons from that bond between this beta carbon and this hydrogen are going to go in between this bond right here to form the double bond. So let's see how that looks like. So again, this is taking the H. This electrons right here between this bond is going to go in between this bond to form our double bond. And you can see that this shortcut that I just said kind of led us to our stated product, where this is tetrasubstituted. Is there any questions on that? Okay, so somebody asked, does it matter the orientation of the H and the CH3? So yes, we're actually going to talk about that. So for E1, it doesn't, right? Because there's a carbocation here, but for E2, it's going to matter whether the H is anti or syn to the leaving group. In this case, it doesn't matter because we have the formation of the carbocation. But we'll talk about that when we're talking about E2 and why it's important for E2. But in this case, it doesn't matter. Okay, is there any questions so far in this mechanism? Okay. Move on to E2. So E2 is going to be similar to SN2 in some aspects. Again, we said SN2 occurred in a concerted mechanism or concerted reaction. E2 is going to be the same. E2 is going to be concerted. So the steps are going to occur at the same time. There's going to be no formation of a carbocation. So for E2, we don't have to worry about methyl shifts or hydride shifts because those happen when there's a carbocation. Let me drink water real quick. So similarly to SN2, right, we had said SN2 involves strong nucleophiles. In this case, this is going to involve strong bases, again, because we're focusing on basicity, because those are the ones removing the H's. So E2 involves strong bases. And similarly, like SN2, it's going to be bimolecular, meaning it involves 2 molecules in the rate. So alkyl halide and the nucleophile. Again, nucleophile and basicity are kind of similar, but we can also just say base instead of nucleophile in this case. But again, they're kind of similar, so we can just base/nucleophile. In this case, one of the main points here that is important that I mentioned in the other slide, right? That's going to be important for this reaction, not so much for E1, but for E2 it is. So the leaving group must be anti to the H that is being removed. And what do I mean by that? Okay, so it's supposed to be 3. Okay, so I mean that this H, if we focus on this H as the one that's being removed, and the leaving group right here, they're on the same plane, but they're anti to each other, right? So in the case that you can't have them be anti to each other, then this reaction won't occur. And we're going to look at the mechanism to kind of go into more detail into how or like why this is important. But yeah, is there any questions so far before we go into the mechanism? So we're going to go into the mechanism of this reaction right here. So here it is. Again, we have the base right here. And the base was Na and then this, but this is just in solution. So right now, don't worry about this one, just worry about the base and our alkyl halide. I've highlighted the things that are, the substituents that are dashed, right? So the blue ones are dashed and wedged are the yellow, and you'll see why that's important in a moment. So we have our hydrogen right here that's going to be removed, right? And just to reiterate, the reason why I chose this hydrogen is because this is the one, so this is the alpha carbon right here, because the B is attached to that carbon. So this is the carbon where the leaving, sorry, Br is attached, where the leaving group is attached. So the carbon where the leaving group is attached is the alpha carbon. And then those carbons next to it are beta. So this is a beta carbon. This is a beta carbon. So we had 2 carbons to choose from. But if we do what I had said in the other slide, kind of look at how many hydrogens are attached to each. So in this beta carbon, there's only 1 hydrogen attached. In this beta, there's 3 hydrogens attached. So we want to remove the H from the carbon, the beta carbon that has these hydrogens. So we're going to go with this one right here. So we're focusing on the hydrogen that is in red. And it is anti, again, anti meaning they're on the same plane, but like opposite. So this is going up, down from the bond. And we'll talk more on that based on rings in a moment. But for now, does anyone have any questions on what I mean by anti? Does it make sense? Any questions so far? You guys are good? Okay. So, right, we're talking about E2 reactions right now. So we have our base. The base is going to remove an H. So this base is going to remove this H. Those electrons between that bond, between this hydrogen and this beta carbon, are going to go towards in between these 2 bonds to form the double bond. And it's in between, right? Because these electrons are being shared, and that's what a double kind of is. And then what's going to happen is that this Br is going to leave. So it's going to look like this. This arrow is taking the H. This electron is going between this bond right here. And then the Br leaves, the leaving group leaves. Right, so then now we form right here our alkene. So again, we know alkenes are planar. So the reason why I highlighted the dashes in blue is because you can see they ended up on the same side. So you can see these 2 are both at the same side, and these yellow ones are at the same side. So it's important to also look at what is wedge, what is dash, and what side these substituents are going to end up at. So is there any questions on how I got this? Okay, and then we have drawn the base here with an H because it removed that H. We know Br left with those electrons, so it's going to be Br minus. So we have Br minus, but we also had Na plus, so I just drew NaBr. But again, both of them are ions, so I just did a parenthesis right there. Any questions? comments, concerns, anything? This makes sense to everyone? Okay.
Okay, I'm sorry, I have a question.
Yeah.
Could you please re-explain why the right side has more hydrogens?
Yeah. So let me zoom in here. So again, we're focusing on the beta carbons and the the beta carbons and the hydrogens attached to those beta carbons. So again, this is our alpha carbon right there. And the alpha carbon is the one where the leaving group is attached to. So the leaving group is attached to that carbon, so that's why it's alpha carbon. And then the carbons right next to it are the beta. So this carbon right here is beta carbon. This carbon right here is beta carbon right there. Again, because it's right next to it, like directly next to it. And then we're gonna look at the hydrogens that are attached directly to that beta carbon. So our beta carbon is that one right there. And you can see right here, it's attached to 3 hydrogens. So 3 hydrogens, as opposed to this carbon right here, this beta carbon right here is only attached to 1 hydrogen, right? Because this is a C and this is a C. So we're looking at what's directly attached to it. So we're not going to focus on these hydrogens right here, only what's directly attached to it. So for this one right here, this beta carbon right here, there's only 1 hydrogen directly attached to it. Versus this one right here, this carbon right there has 3 hydrogens directly attached to it. Does that make sense?
Yes, thank you. I didn't realize that that was the beta carbon. I had it mislabeled. Thank you.
Okay. Any other questions? Okay. So I want to do an example when state symbol is broken, and this is when it being anti, so like the leaving group being anti to the H is important. So let's go over this example right here. Let's zoom in. So first, let's label which is our alpha hydrogen, our alpha carbon, and which is our beta carbon. So this is our alpha carbon. I know this looks wonky, but that's an alpha. And again, it's because that carbon is attached to the leaving group. So that's the alpha carbon. And then we have our beta carbons that are directly attached to that alpha carbon. So we have a beta here. We also have a beta here. Let me actually highlight those. So this is a beta carbon. This is a beta carbon. This is a beta carbon right there. And then the next step would be kind of figuring out where the H is going to be removed from. So then we have to look at how many hydrogens are attached to that beta carbon. So in this one right here, there's 2 hydrogens attached, right? So 1, 2, and this is a carbon, so that's why it's 1, 2. And then let's focus on this carbon right here. There's only 1 attached to it. So let's write that down. 1 hydrogen. And then let's look at this one. There's 3 hydrogens. So we're going to want to remove it from this beta carbon. Does that make sense to why? Right, this one has the least hydrogens. So this one is going to lead us to our state product. However, in this case, there's going to be an issue because I said, right, that the leaving group, which is Br, has to be anti to the hydrogen being removed right here. Because you can see both of them are dashes, right? So they're not anti, they're actually syn, right? They're pointed to the same direction. So you can't remove that H because of the fact that it's not anti. So in this case, we can't remove it from this one right here. So we're gonna discard that. And our next best option is gonna be this 2H, or this beta carbon that has 2 hydrogens attached to it. Any questions so far? So if the leaving group and the hydrogen that's being removed by the base is not anti, it's not, that H cannot be removed. Okay, and this is only important for E2, not for E1. Okay, so we're gonna then focus on this one. We can see that there's an H that is wedged and one that is dashed. So this wedge H right here is anti to this ER. So then we can remove it from that beta carbon. So let me erase this. So then that base is going to go and remove that H. Then the electrons between that bond is going to go directly in between this bond right here. And as it does that, this leaving group is going to leave. So now we have formed this double bond in between this beta carbon and this alpha carbon right here. But notice how it's not following Sate's rule, right? If we would have formed it between this right here, we would have had a tetra substituted, right? And it would be tetra because it has 1, 2, 3, 4. So if it would have formed between this one and this carbon right here, we would have had a tetra. But because it wasn't able to remove that H because it's not anti, then it went to the next best thing, which was this tri-substituted one. So this is not necessarily following Sate's rule, right? This is still stable. Oops, let me get highlighter. This is still stable, but it could have had a more stable one if it was tetra, but it wasn't able to be formed because this H was not anti to the leaving group. So now we have a tri substituted right here. Is there any questions? Okay, so in this case of this reaction, because we were not able to remove that H, that would have given us Sate's product. We went to the next one, right? In this case, it gave us this product. Any questions? Okay. And I just want to make one more note before I pass it on to Jennifer. I'm not going to go much detail into this, but just know that if we have a reaction, right, we have a base. Again, bases and nucleophiles are kind of related. They're kind of similar, but obviously they're different in some aspects. There's some products where SN reactions, so substitution reactions, elimination reactions, compete such that where you're able to have both substitution products and elimination products, right? So in this case, it's not an actual reaction. This LG means leaving group, this B means base. So we're not working with any actual molecules right now, just in order for you guys to see that sometimes these reactions are going to compete and you're able to have both substitution and elimination products. And when that happens, if the reaction has heat, so this triangle here is for heat, so you can just heat. When there is heat on the reaction, the elimination product is going to be favored, such that sometimes they ask for the major product of a reaction, right? So in this case, if there is heat, we can label elimination product as a major product. And then we can label this as a minor. But for right now, I just wanted to introduce this concept of heat favors elimination products when they are competing. But yeah, is there any questions about anything I have covered so far before I move it on to Jen? I'll move it on to Jen.
All right, thanks, Ashley. Okay, so I just wanted to do a very quick overview of what we just learned in lecture today. So just comparing E1 and E2. So for E1, it's essentially the beginning part is the same as an SN1 reaction. It's a first order reaction. So the rate of the reaction is only dependent on our acyl halide, or more generally just our acyl substituent with that leaving group connected to it. And so it's going to be a two-step reaction. So that first step is the exact same thing as SN1. It's just forming that carbocation. And so because of that, tertiary molecules are going to be much more favorable just because of that carbocation stabilization. And so because of this, E1 usually involves weak bases because that carbocation is such a strong acid. Because you remember, carbocation doesn't have a full octet. So it wants to give up one of its hydrogens so it can accept those electrons to form a double bond and get a full octet. And so because of that, we only need very weak bases in order to do this reaction because we've done all the work in that first step. And so because E1 is essentially that first step is just like SN1, it can also have carbocation rearrangement. So that was like that methyl shift, that hydride shift that you saw on Monday. And so E2, just like SN2, is going to be a second order reaction where the rate of the reaction depends both on the acyl halide and the nucleophile. So I've just denoted it here like this. And so this is also going to be a considered reaction. And so because your base is just going to be attacking your acyl halide, that's not a very strong acid. So you need a very strong base usually in order to go through this reaction. And so another thing to keep in mind is just because of the mechanism of E2, the beta hydrogen that's removed must be anti to the leaving group. So this will just move. Okay. So just as a quick review, looking at this molecule. So this is essentially just a simple methyl group connected to a leaving group. Could this molecule undergo E1, E2, or both? So one thing to look at is to look at what carbocation would be formed if you were to take off this Br. And then see, would this be favorable for E1 or would this be more favorable for E2? Okay, this is actually a really mean question because this is actually a trick one. So one thing to keep in mind, that one thing that makes elimination very different from substitution is that elimination requires the removal of beta hydrogens. So in this case, we only have an alpha carbon. There's no beta carbon, right? There's only this one carbon here. It's connected to hydrogens. So since there's actually no beta hydrogens, this can't undergo elimination. So if you just see like a methyl connected to a halogen, that cannot undergo E1 or E2. So yeah, so moving on to a more reasonable question. So yeah, beta elimination is impossible in this case, but in a different reaction. So looking at this molecule, so let's see what's going on here. I've drawn out all the hydrogens just so it's clear. So this carbon over here, that's going to be our alpha carbon because it's directly connected to a leaving group. In this case, there is a beta carbon. So could this molecule undergo E1 or E2? Once again, look at that alpha carbon.
Would it prefer E2?
That's a good guess. So look at this carbon right here. So is this going to be a primary, a secondary, or a tertiary carbon? You were right, by the way. I'm just stressing this point.
It'd be primary?
Yeah, primary. And so is that going to be a very stable carbocation? Sorry, I can't speak today.
No, it wouldn't.
Yeah, it wouldn't. So exactly. And so because of that, we almost never see primary acyl halides undergo E1. Like I guess it would technically be possible, but it would happen at such a low rate that we usually just don't consider it. So for primary acyl halides, for like the point of this class, we can just say that only E2 is possible. So yeah, okay, and then moving on to this carbon. So for this alpha carbon, is this going to be primary, secondary, or tertiary?
Secondary?
Yeah, it's secondary. So do you think this could undergo E1, E2, or both?
Could it be both?
Yeah, that's exactly right. So this molecule could undergo both reactions. So you could either just take off this hydrogen, take off this Br by itself and make a carbocation and then take off this hydrogen, or you could take this off this hydrogen and this leaving group in the same step. We'll go more into detail about cases where there are two competing reactions later in the course, but for now you can just think for secondary and tertiary acyl halides, both E1 and E2 are possible. Okay, And this is honestly just the reaction that Ashley went over. I just wanted to stress one difference between, one thing about Zaitsev's rule is that it talks about which is going to be your major product. So in the actual course, oftentimes you'll have to identify all the products, so even the major and the minor products, and Zaitsev's rules will just help you identify the major product. But one thing about anti-conformation is that if it's not in the anti-conformation, none of it is formed. So in that case, that's why Zaitsev's rule doesn't even come into play, because Zaitsev's rule just tells you of your possible products, which one is the most favorable. But if this product here isn't formed at all, it's not going to be favorable or unfavorable. It just doesn't appear. It doesn't compete at all with this reaction, with this product. So we don't even consider it. Okay, and then I'm just going to walk through some examples, but yeah, once again, E2 anti-conformation completely overrides Zaitsev's rule. You don't need to consider this conformation at all, just because it doesn't occur. Okay, and so one thing I wanted to stress was that E1, that first step, that carbocation formation, because of that, it also has hydride shifts. So looking at this reaction of this molecule, so this is going to undergo E1. So you're going to take off, this is your leaving group right here, this is your alpha carbon, and you've got 2 possible beta carbons. So looking at this reaction, what is the reaction you would expect to see if there wasn't any hydride shifts? Where would you expect to see the alkene? Would it form here or here? So in this situation, this is where Zaitsev's rule would come into play. So you need to think of the alkene form, which one is going to be the most substituted? This one here, or this one here? This first one or the second one? Okay, this can be really tricky to look at. So let's just go do this together. So if you would form this alkene here, it would have, and so this BR would come off. So it would just have 1, 2, 3 attached carbon groups. And this one, if you would form the alkene here, it would just hydrogens here, so it'll only be 1 carbon group. So this one would actually be the most substituted. So if there wasn't any rearrangement, you would expect to see this product. But actually, this product is a very minor product. You wouldn't see it a lot. And so to look at the major product, to understand the major product, we need to look at the carbocation, because that carbocation formation is like the rate determining step. What makes a reaction favorable is dependent on that carbocation stability. So the more stable your carbocation, the more likely that product for E1. So we need to consider carbocation rearrangement. So I've just drawn out the potential carbocation in this reaction here. So you would expect to see this carbocation, right? If you take off this Br, you would just be left with this carbocation right here. So this would be, what kind of carbocation is this? Is this primary, secondary, or tertiary?
Secondary.
Yeah, exactly. It's secondary. So it's pretty stable, but it's not the most stable that it could be. So if you remember from Monday's lecture, so hydride shift is essentially where you take a hydrogen from a nearby carbon, a carbon that has more substituents, and you just move it over there. And so you can create a more stable carbocation. So I've just drawn out the carbons here for these molecules. So I've drawn out the hydrogens here for this molecule so you can see what's going on. So which hydrogen do you think you can move in order to make a better carbocation? So it's going to be an adjacent carbon only. So it's either going to be this one or one of these 3. Which one do you think we should move to make a more stable carbocation?
The one in between the H up top.
Yeah, exactly, this one. Because if you were to take this hydrogen off, you would create a tertiary carbocation. But if you were to take this one off, you would create a primary carbocation, and that would be even less stable. So that's not going to happen. So like as you said, we move this hydrogen over here. So now there's 2 hydrogens here. This carbon has a full octet. It's uncharged. It's completely happy. And now this carbon here is what has the unfilled octet. It only has 6 electrons and it's electron deficient. So it has that positive charge. And now this is going to be your tertiary carbocation. And this reaction right here, this carbocation rearrangement, it happens pretty spontaneously just because how the difference in stability here. So you didn't need to wait. There's no like reactants or like energy input or anything you need to worry about. This reaction happens very commonly. And so from here, we can just do a regular E1 reaction. So looking at the reaction here, I've labeled the beta carbons right here. Sorry, the beta hydrogens right here. So which beta hydrogens do you think you should move? This one here or one of these two? Using the trick that Ashley just showed you. Another way to think about it is if you were to create an alkene either here or here, which one's going to have the most substituents? So which one's going to be the most stable?
Would it be the hydrogen on the ring?
Exactly, right. Because using Ashley's rule, there's one hydrogen here, there's two hydrogens here. You need to remove the hydrogen, the hydrogen from the carbon that has the fewest hydrogens. And also just thinking it from substituents, if you create an alkene here, it would have 1, 2, 3, 4 substituents. If you remove the hydrogen here and formed alkene here, it would only have 1, 2, 3 substituents. So this one over here, that's going to be the much more stable product. This is going to be your major product. So right here. And so yeah, this would be your major product. So you would, if you did run this reaction, when you run elimination reactions, usually it does form all the possible products. It just forms your major product in the higher concentrations. So I guess it would be possible to see this one just in very, very small amounts. So we wouldn't really need to consider it. This is the one that this is your major product. This is the one you usually focus on. Okay, so let's do this practice again using acyl shifts. So in cases where there isn't a hydrogen you can move, you can also move an acyl group in order to create a better carbocation intermediate. So let's look at this reaction. This is pretty similar to what we just did before. So what do you think we can move in order to create a more stable carbocation? And remember, this is going to look very similar to the one before. If we just take off this Br group, this leaving group, we'd be left with a secondary carbocation. And so what can we move around, do you think, to make a tertiary carbocation?
That methyl group to the left.
Yeah, exactly. It's going to be a very similar reaction. So looking at this, this would be the secondary carbocation we would first create after this Br group is left, has been taken off. And so through carbocation rearrangement, we just move that methyl group over one and create this tertiary carbocation, which is much more stable. And so this carbocation is going to go on to create our major product. So I'm not going to draw out the mechanism for the sake of time, but here I've just run out all the possible beta hydrogens. So which hydrogen do you think we're going to take off? These two here or this one over here? I guess we could also consider this one over here, but these ones are more substituted anyway, so we'll just focus on these two.
Would it be the rightmost one?
Yeah, exactly. Because there's only one hydrogen here as opposed to the two hydrogens here because there are more substituents here. So yeah, you would take it out from the right. So I've just drawn out the reaction again. So your base would come in and take out that hydrogen and then form a double bond right here. Okay, and I believe that is all the examples I had. So you guys are free to leave. But if you guys have any questions, you guys are free to stay around. But thank you guys so much for coming today.